So today's topic is normal distributions. Open your normal distribution file on your Inspire and go directly to page 1-2. So let's imagine that we were able to determine the height in centimeters of all 10-year-old children in the United States. The average height of 10-year-olds is approximately 138 centimeters. If we were to create a dot plot that showed all the heights, most of the heights would be near the average or mean of 138. If we then draw a smooth curve joining the top dot for each height, we would draw a bell-shaped curve called the normal curve. When you go to page 1-3, you'll see a normal curve for that data of 10-year-olds' heights in centimeters. So go to page 1-3, and here's a bell curve that I created from the data. Notice that in the middle is the height of 138 centimeters, and most of all the heights of all the children are near that 138. The majority under the curve. In calculus, you'll talk about that as area under the curve. Here we're just looking at the most space, I guess, under the curve. Okay, so if you move to page 1-4, scientists have found that large sets of data that occur naturally, such as heights, weights, or shoe sizes, have a bell-shaped or normal curve. The highest point of the normal curve is at the mean of the data. The normal curve is symmetric with respect to a vertical line through the mean of that distribution. So the mean is always in the middle of a normal distribution, of a normal curve, normal model. Lots of different ways to say it. Okay, on page 1-5, a normal distribution is a set of data that can be represented by a normal curve. Not every set of data is normal, but many are, and that's what we're going to talk about today, are those special ones. For a normal distribution, when we have a normal distribution, the following relationships exist. First of all, both the mean and the median are in the middle. So the mean and median are in the middle. Second relationship, 68%, let's say approximately, 68% of the data lie within one standard deviation of the mean. So 68% of the data surrounds the mean, and it's within one standard deviation of the mean. I'll give you examples of what that means in a few minutes. The next relationship is that approximately 95% of the data lie within two standard deviations of the mean. And I don't want to type it all out, so that's why I'm abbreviating there. And the final relationship with our normal model is that approximately 99.7% of data lie within three standard deviations of the mean. So when we have data that's normally distributed, most of it will be within three standard deviations of the mean. It won't vary much from the mean. And you can see that in that picture from page 1-3. The majority of your data is centered right around the mean. There's not a lot of variation. Okay, let's go to page 1-6 for some samples. 1-6 and 1-7 are two examples. We're going to do those together with the Elmo in a minute. You're also going to want to take a glance at your Regents reference sheet so that we can look at that normal model that they give you. Notice what's given to you that you don't have to memorize, and so we can refer to that and use it to help us solve problems. So on our Regents reference sheet, they don't give us everything. The way it's labeled is it's labeling the x-axis or the bottom as the number of standard deviations from the mean. Notice then that in the middle there's 0. That is the mean value. The mean is always in the middle of your normal model. And then state ed, for whatever reason, likes to give you the percentages in half standard deviations. We generally don't care about the half standard deviations. We care about the 68, 95, 99, 7 rule, which deals with whole standard deviations. So when you go 1 standard deviation on either side of the mean, there's 68%, 2, 95%, 3, 99.7%. Most of the time you can ignore those halves. So let's do some samples. A set of data is normally distributed. As soon as you read that, you draw the normal curve. They don't have to be perfect, it's just a guide for you. With a mean of 50, so put 50 in the middle, and a standard deviation of 2. So we add 2 3 times to the right and subtract 2 3 times to the left of the mean to complete our normal model. So I'm showing x plus 1 standard deviation, x plus 2 standard deviations, and x bar, mean, plus 3 standard deviations. And then I'm subtracting 1, 2, and 3 standard deviations on the left as well. You don't have to label it like that every time. I do that for you for the first example so that you understand where the numbers are coming from. Okay, now that you have a well-labeled picture, you can start answering questions about it. So for question number 1, what percent of the data values are less than 50? Well, 50 is our mean. And 50, the mean, cuts the model in half, which means 50% of our data values are less than that 50. It's hot. What percent of the data values are between 48 and 52? Well, find them on your normal curve. And again, our 68, 95, 99, 7 rule says that between 1 standard deviation below and above, I have 68% of my data. Now that's approximate, that's fine for us. If you're really, really picky and want to be perfect like State Ed, you can go to their normal curve on your Regents reference sheet and add up all those percentages between 1 standard deviation below and 1 above. When you do that, you'll get 68.2%. I'm not worried about the 0.2%. You'd get credit for either. So for number 3, what percent of the data values are between 46 and 54? Well, I go back and look at my normal curve, and I notice that those are 2 standard deviations from the mean. My 68, 99, 95, 99, 7 rule says that that's approximately 95%. Again, that's just fine for us. But again, if you really want to use your Regents reference sheet, you can add up all those percentages within 2 standard deviations of the mean. And so you can just add those up from the more recent 68.2 and you get 95.4. 95 is close enough for us. Finally, what percent of data values are less than or equal to 46? So you go back to your normal model, find the value of 46 that you've already labeled, and notice that that's less than the mean minus 2 standard deviations. So I go back to my formula sheet. There's my negative 2 standard deviations mark. Add up those percentages. And I get 2.3%. Okay, our last example for the day, we have a standardized test. The scores are normally distributed with a mean of 60 and a standard deviation of 6. Here I tell you to draw and label the normal model, but you would do that anyway of your work when you read normal distribution. So again, the mean goes in the middle, and I add standard deviations 3 times to the right and subtract the standard deviation 3 times to the left. A completely well-labeled normal model also includes the 68, 95, 99, 7 rule. So I just label that inside my curve. 68% is within 1 standard deviation of the mean, 95 within 2, and 99.7 within 3. And again, now I can answer questions based on that picture. So number 2, of the data, 84% of the scores are at or below what score? Well, think about your normal model. The mean cuts it in half, that's 50%. I need to find about 34% more. Well, that takes me to 1 standard deviation above the mean. So 84% of the scores are at or below a 66, the number you put at 1 standard deviation above the mean. For 3, we have 16% of the scores are at or below what score? Well, 16%, not really positive where that is, but I have my Regents reference sheet, and I can start adding percentages from the left to the right until I get to about 16%. So I've got my 0.1, 0.5, and 1.7, which gave me 2.3 earlier. I can now add to that 4.4, and I'm not quite at 16 yet, so then I add to that 9.2, straight off of my reference sheet. You don't need to memorize these percentages at all. When I add that final 9.2, I get 15.9, close enough to 16 for statistics. So I go to 9.2 on my Regents reference sheet. That is at the 1 standard deviation below the mean line. And on my current picture, that is 54. The last question, if 2,000 students took the test, how many would we expect to score at or below 48? Well, 48 on my picture is 2 standard deviations below the mean. Go back to your Regents reference sheet, or the earlier question that told us that 2.3% of my values on my normal curve are at or below 2 standard deviations below the mean. So you're just going to find 2.3% of 2,000, which takes you back to middle school percentages. So 2,000 times 0.023 is 46. You expect 46 students to score at or below a 48.